Welcome to Complex Analysis. Today we are going to explore one of the most beautiful and fundamental concepts in all of mathematics, the Cauchy-Riemann equations. If you have ever wondered what makes complex calculus different from standard calculus, this is the exact moment you find out. We will build this from the ground up, so do not worry if it sounds intimidating right now. Let us dive in and discover the hidden rules that govern the complex plane. Now that we are ready, let us start with a simple analogy. Imagine you are flying a drone using a remote control joystick. The joystick can move left to right, which we will call the X direction, and forward to backward, which we will call the Y direction. The drone responds by moving in the sky. Its east to west position is U, and its north to south position is V. In standard mathematics, you could program the drone so that pushing left only changes U and pushing forward only changes V, completely independently. But in the world of complex numbers, for a function to be smooth or differentiable, the controls are magically and strictly locked together. The way the drone's east to west position changes must perfectly match how its north to south position changes. Any complex function can be written as f of z equals u plus I times v. The Cauchy-Riemann equations are the mathematical rules that force these two parts to move in perfect harmony. This strict, invisible linkage we just discussed is captured perfectly by the Cauchy-Riemann equations. Conceptually, these equations tell us that the rate of change in the real direction must perfectly balance the rate of change in the imaginary direction. Let us look at the symbols. The variable u is the real part of our output, and v is the imaginary part. The variables x and y are the real and imaginary parts of our input. The first equation states that the partial derivative of u with respect to x must exactly equal the partial derivative of v with respect to y. Physically, this means the rate at which the real output changes as you move horizontally must exactly match the rate at which the imaginary output changes as you move vertically. The second equation states that the partial derivative of u with respect to y must equal the exact negative of the partial derivative of v with respect to x. If a complex function is differentiable, these two equations must absolutely hold true. Before we prove why these equations work, let us see them in action with a concrete example. We want to determine if the basic polynomial function f of z equals z squared satisfies the Cauchy-Riemann equations. We are given the function and we are asked to find its partial derivatives to check for differentiability. To solve this, our first step is to express z squared in its expanded rectangular form. We substitute z with x plus I times y. This is the fundamental first step in any problem where we need to separate a complex function into its real and imaginary parts. Next, we expand the squared binomial using standard algebraic rules. This gives us x squared plus 2ixy plus the quantity iy squared. We now have three distinct terms to work with. Continuing with our expansion, we must now simplify the final term. We know that the imaginary unit squared, I squared, is defined as -1. So the term iy squared transforms into -y squared. This removes the imaginary unit from that specific term, making it a real number. Now, we group the terms without an I together in parentheses to form our real part. And we factor out the I from the remaining term to form our imaginary part. Our function is now perfectly separated. The real part u is x squared minus y squared. The imaginary part v is 2xy. We are now ready to take their partial derivatives. Let us calculate the four required partial derivatives. First, we look at the real part, u, which is x squared minus y squared. To find the partial derivative of u with respect to x, we treat y as a constant. The derivative of x squared is 2x and the constant y squared becomes 0. So we get 2x. Next, differentiating u with respect to y, we treat x as a constant, giving us -2y. Now we move to the imaginary part, v, which is 2xy. Taking the partial derivative of v with respect to x means we treat y as a constant multiplier. The derivative of x is 1, leaving us with 2y. Finally, differentiating v with respect to y leaves us with 2x. We now have all four pieces. Now, we compare our calculated results against the Cauchy-Riemann equations. The first equation requires the partial derivative of u with respect to x to equal the partial derivative of v with respect to y. We found both of these to be 2x. Because these match perfectly, the first condition is satisfied. We then check the second equation. The partial derivative of u with respect to y is negative 2y. This must equal the exact negative of the partial derivative of v with respect to x, which was 2y. Indeed, negative 2y equals negative 2y. Since both equations hold true for all possible values of x and y, we can confidently conclude that the function z squared is differentiable everywhere in the complex plane. Let us look at another example. We will test the complex conjugate function f of z equals z bar to see if it satisfies the Cauchy-Riemann equations. The complex conjugate is a very simple operation that just flips the sign of the imaginary part. Visually, it reflects a point across the horizontal real axis. Because it is so simple, it might seem like it should be smooth and differentiable. By definition, the function is x minus I times y. We can immediately identify the real part u as simply x. This means the horizontal output perfectly matches the horizontal input. The imaginary part v is negative y. It is crucial to include the negative sign here. Let us find their partial derivatives next. We take the partial derivative of u with respect to x, which is simply 1. This tells us that as the input moves right, the real part of the output also moves right at the exact same speed. Next, the partial derivative of v with respect to y is negative 1. This tells us that as the input moves up, the imaginary part of the output moves down at the same speed. We immediately see a fatal problem. The first Cauchy-Riemann equation requires that these two derivatives must be exactly equal. However, 1 does not equal negative 1. Because this fundamental equation fails, the complex conjugate function is not differentiable anywhere. This proves an important lesson. Visual simplicity does not guarantee complex differentiability. Now that we have used this formula, let us understand where it comes from. To truly understand why the Cauchy-Riemann equations exist, we must derive them from the fundamental definition of a derivative. The derivative of a complex function is defined by a limit as the change in the input, denoted as delta z, shrinks down and approaches 0. In this foundational formula, f prime of z represents the complex derivative we are trying to find. Because we are operating in a two-dimensional complex plane, delta z can approach 0 from any direction whatsoever, horizontally, vertically, or diagonally. For the derivative to mathematically exist, this limit must give us the exact same final answer regardless of which path we take to get to 0. We will test two specific paths. Let us first test a path that moves purely along the horizontal, real axis. By setting the imaginary part of our tiny step to 0, delta z becomes simply delta x. We plug this purely horizontal step into our main derivative formula. At the same time, we separate the function into its real component u and its imaginary component v. By grouping the real parts together and the imaginary parts together, a beautiful pattern emerges from the algebra. These two separate limits are exactly the standard calculus definitions of partial derivatives. The first fraction describes how u changes as only x changes, and the second describes how v changes as only x changes. This gives us our first complete expression for the complex derivative, calculated by moving horizontally. Now, we must perform the exact same process but taking a completely different path. This time, let us approach 0 purely along the vertical, imaginary axis. We set the real part of the step to 0, so delta z becomes I times delta y. We plug this purely vertical step into the original derivative limit formula. Notice that the denominator now contains the imaginary unit I. We group the u terms and the v terms into separate fractions. To simplify, remember that dividing by I is mathematically identical to multiplying by negative I. In the second term, the I in the numerator and denominator perfectly cancel out. Rearranging the terms to put the real part first, we get our second expression for the derivative, calculated from the vertical path. We now have two different expressions for the exact same derivative. Because we assume the function is differentiable, the derivative must be a single unique value. Therefore, the result from our horizontal path must perfectly equal the result from our vertical path. We set these two expressions equal to each other. This is the crucial moment of the derivation. For two complex numbers to be truly equal, their real parts must be identical and their imaginary parts must be identical. By equating the real parts, we get the first Cauchy-Riemann equation. By equating the imaginary parts, we get the second. Together, these form the absolute necessary conditions for a complex derivative to exist. We have successfully proven the equations. Let us visualize the core concept of the derivation we just completed. On the screen, you see the two-dimensional complex plane. The horizontal axis represents the real part, x, and the vertical axis represents the imaginary part, y. In the center is our starting point, z. Because the plane is two-dimensional, a limit can approach this point from any angle. The horizontal arrow shows our first path, where only x changes. The vertical arrow shows our second path, where only y changes. By forcing the horizontal approach and the vertical approach to yield the exact same mathematical result, we naturally uncovered the Cauchy-Riemann equations. This diagram shows exactly why complex differentiability is so much stricter than real differentiability. So, we have proven that these equations hold. This brings us to an important question. Why do we care so deeply about them? In the real world, engineers and physicists use complex functions to model physical phenomena that flow. This includes heat moving through a metal engine plate, water flowing around a bridge pillar, or invisible electric fields surrounding a high-voltage wire. For the mathematics to accurately predict these physical flows, the functions we use must be analytic, which is a technical term meaning they are differentiable and smooth over a region. The Cauchy-Riemann equations are the ultimate, definitive test to check if a function is analytic. If a function passes this test, it unlocks a massive toolbox of mathematical shortcuts, allowing us to solve complex real-world engineering problems that would otherwise be entirely impossible. We have covered a lot of ground today. So let us summarize the most important ideas. First, remember that in complex analysis, the real and imaginary parts of a function are not independent. They are strictly locked together. Second, the Cauchy-Riemann equations are the mathematical rules that define this linkage. We saw that they emerge naturally when we force the horizontal and vertical derivative paths to equal each other. Third, these equations are the absolute test for differentiability. As we saw with the complex conjugate, visual simplicity does not guarantee a function is smooth. You now understand the fundamental rules of the complex plane. These equations are your essential gateway to the most powerful tools in complex analysis. Great job following along.